All right, let's get a little practice going here. Take the derivative of those two functions. Obviously, the left one, what would we use? Product rule, and the right one? Quotient rule. So while you're calculating that, I'm going to talk a little bit. The reason I'm having you do this is because we talked about this already. There is another way to do this function, take this derivative, other than using the product rule. What would it be?
Multiply the two things out.
Yeah, you can multiply that beast out. Not recommended, but possible. Today we're going to learn an alternative to the quotient rule, which some of you may like, some of you may not like. Pregunta.
So if we don't like this alternative, do we have to use it?
You don't have to do anything. This is America. Fight the power right on. Unless it specifically says use the quotient rule to find this derivative, you can use whichever technique you'd like. My job is to just give you a bunch of weapons to use in your arsenal, and therefore when a problem comes around, you got it under control.
Does it go with those sound effects?
Those are optional. They do cost a little extra, but I mean it's like, you know, it's like GPS on a car. You know, you don't get it for free. It's a nice feature, but you don't get it for free. Don't bother simplifying that much. Just, you know, you get it done, you get it done. First times derivative of second, second times derivative of first. And just leave it there. We're good. Quotient rule, however, is more important. See if you remember that. Because on the quiz, I saw some people were doing quotient rule incorrectly. The biggest problem is you got them reversed. You did the wrong way, which would be the numerator times the derivative of the denominator first, and it's the other way around. So we'll do this again just to make sure everybody has it under control. Because I don't think I have the answers. Oh, I do. Cool.
The quiz is graded.
How's it going?
The quiz is graded.
Oh,
Are they online?
no. Just got it finished last period. So I'll try to get the scores online ASAP. Worst case scenario, I do an 8th period. I'm giving another quiz for GO 8th period, so I'll have them up by then. Okay. If you were to continue with the product rule, simplify everything, boom, you'd get that. And then this monster, you would get that. Question, sir?
Can you repeat what you said that people were getting confused on?
Oh, doing the quote. I'll do this one with you, and I'll show you what people are doing incorrectly. As soon as I find my pen, here we go. Oh, crikey. Great, this will be in the slideshow now.
So do you have to do that like once a day?
No, I have to do it like 5 times a day. Okay, so very quickly, quotient rule. We would get the denominator on the bottom squared. Probably want to start with the Gezinterbar. Then bring that denominator up to the top, times the derivative of the numerator, minus, big brackets, the numerator, times the derivative of the denominator. And Mark, to answer your question, what people are doing is they're getting these two things switched, doing it backwards. Okay, that's why I showed you, put the denominator on the bottom and square it, then bring that denominator up to the top so you know not to take the derivative of that. And if you look at my answer, then you can see there's my denominator. Remember, don't multiply out denominators ever. And then this would be my numerator if I was to simplify all that stuff. Distribute the 2x to each of the things in parentheses. Distribute the 3. Be careful with the minus sign. Add it all up, and you end up with that final answer. Okay? Problems? No? Great. Let's move on then to the chain rule. Dun, dun, dun. All right. Chain rule is used mainly to take the derivative of composite functions. However, we can also use it to simplify a quotient rule. To that in a second. The difficulty in, well, there's two parts of chain rule. The function or the rule itself is fairly tricky, but simplifying that algebraically is going to be difficult for some of you also. And of course, we got to bring some trig into it. What happens when you want to take the derivative of something like the sine of 2x? And then you should be able to recite the state capitals. Which there's no way I could do that. Okay, chain rule, here we go. Functions within functions. So if we look at something like this, x squared plus 1, no problem. You can take the derivative of that and get 2x. Sine of x. These are all easy. We've done all these already. However, now we start looking at functions on the right where we have composite functions. So if we look at the first one, for instance, the square root of x squared plus 1, how many functions are involved there?
Is it just one?
2.
Oh,
Why 2? It's the x squared plus 1, and that function is inside the square root function. This is an important concept. You have to be able to recognize how many functions because it will make your life a lot easier. So for instance, sine of 6x, how many functions? 2. What are they?
6x.
Good. 6x and the sine. Which one's on the inside?
6x.
Good. Okay. Next one down, 3x plus 2 quantity to the 5th power. How many functions? 2. Which one's on the inside?
3x plus 2.
Good. And then this puppy. I mean, it's kind of a tricky question because I got an x over there, but look at tangent of x squared. 2 functions, x squared is on the inside. Okay, if you can recognize that, then the chain rule won't be so bad. If you have trouble with that, you'll struggle a little bit with the chain rule. Yes, sir?
So wait, the bottom one does only have 2 functions?
Well, you got a little bit of ambiguity because you got
Yeah.
the plus sign in there. But if you just look at tangent of x squared, that would be 2.
So what is that whole thing then?
Well, this, I wouldn't even count the x because when you take the derivative of x is 1, you get done with that, and then you move on to the tangent of x.
Okay.
Okay? All right, so here's the fancy schmancy way of describing the chain rule. If I want to take the derivative of a function within a function, forget about this up on top. The Leibniz notation doesn't help as much as the Newton notation. If I want to take the derivative of f of g of x, I take the derivative of f first, leaving g inside, and then we call it chaining on the derivative of the function inside. Okay, so we start from the outside in, like peeling an onion. Like if you were an ogre. That's from Shrek. Big fan of Shrek. Great movie. Have you seen it? Yeah, good movie. Yeah, have you seen them all?
Aren't you making a new one?
Shrek 1, Shrek 2.
There's a holiday one.
Is there a Shrek 3?
Yeah, and there's a
Shrek 3, and then the Christmas special is, the holiday special is really good too.
Seen the one with the godmother versus
I think that's 2. Is that right? The Godmother's in 2?
Yeah.
Yeah.
and the one where they had the Shrek's Got Talent or whatever.
One is with Lord Farquaad.
Right. Which one's 3? I must
I
have
think
seen
that's
it.
the one with the
The talent show.
I think that's one.
There's one. I don't know if the end is like a talent show.
I haven't seen it in
Okay, so in English, take the derivative of the outside function times the derivative of the inside function. So again, like peeling an onion, you start from the outside and you work your way in. Okay. Now they talk about some notation up here. So they give you an FU. What? What's so funny? It says FU right here. What's the problem? Why are you laughing? We're just, look, FU. If that's what you're taking the derivative of, then you need to identify what U is in order to get an FU. What's the problem, Alex? finding the chain rule humorous? Okay. Let's move on. Excuse me, I'm choking. The idea of finding how many functions we have becomes important because you're going to chain on one less than the number of functions. So if you look at the thing that you're taking the derivative of, and there's 4 functions, you're going to chain on 3 times. Okay? 3 functions, chain on 2 times. 2 functions, chain on 1 time. So it's always 1 less than the number of functions that you have. So if we go back to this slide where we had, where we had all these guys, these were all 2 functions. Therefore, you'd only chain on once. That's important because what will happen is you'll see situations where it looks like you can just keep adding the chains on and do another chain and do another chain and do another chain, and you need to know when to stop, Greg.
So when you say chain on 1 less, would that kind of be like the higher order derivatives? Like where?
Yes, kind of.
Oh, okay.
Yeah. So this seems a little confusing, and once you start seeing some examples, it'll make a little bit more sense. Okay, said that already. Great. Okay, so let's do this. 2x minus 3 raised to the negative 2 power. How many functions? How many? 2, right. What are they?
2x minus 3.
And the negative 2 power. Okay, which one's on the inside?
2x minus 3.
Good. How many chains?
1.
1. Okay, good. Everybody good there before we actually start doing the math? Yeah? Okay, because if you can identify those couple questions, if you can answer those couple questions, then the chain rule isn't that bad. So we start with the outside function, and the outside function is raising something to the negative 2 power. So taking the derivative of something raised to the negative 2 power involves what? How do you do it?
Multiply the integer in front by the power and then subtract what it's raised to.
So something raised to the negative 2 power, the derivative of something raised to the negative 2 power would be?
Negative 2.
Times
And-
that thing
And
raised to the,
negative 3rd.
perfect. Okay, so I didn't write it up there, but then for this guy, where's my pen? Okay, so based on what Maggie just told us, we look at the outside function first, bring the negative 2 down of that thing, whatever that thing is, I'll come back to that in a second, and raise it to the negative 3. Well, what's that thing? That thing is the 2x minus 3. Now I need a chain. Because I had 2 functions, I need a chain, and what do I chain on? I chain on the derivative of the stuff inside, which would just be 2. Okay? Are you with me?
Do you need to simplify that?
Yeah. Yeah, that's a whole different animal, which we'll address later. In case you didn't hear him, he asked, do you need to simplify that? And the answer is yes. That's it.
How do you get the 2?
The 2 on the back end?
Yeah.
That's the chain of the function inside. So I took the derivative of the outside function first, that's something raised to the negative 2 power, and that something is this, and I keep calling it something because I don't want to get bogged down in whatever that thing is. And then I have to chain on the derivative of that thing inside. Okay? And then I would simplify that to negative 4 times 2x minus 3 raised to the negative 3 power. Okay, for h, how many functions? 2. How many chains? 1. Which function's on the outside? We'll start with that one first. To the 4th, correct. Okay, so forget about this beast inside. Just take the derivative of anything raised to the 4th power. Bring the 4 down, reduce the power by 1. Of that thing, which happens to be this big, scary quartic. Then chain on the derivative of that big, scary quartic. And it gives you that. Yes.
Would we just leave our answer like that?
For now, yes. Yeah, we'll talk about simplifying later once you get the chain rule under control. Yes, sir.
I still don't get it. Wait, how do you get the second part again? Like,
This guy,
yeah.
this 4x cubed plus 6x plus 2 is the derivative of the function inside. That's what we call the chain. You're chaining on the derivative of the function inside. Okay, this one's going to be a little ugly. So before I even proceed, let's make sure you understand what's going on. I've got two functions that are multiplied together. However, each of those functions are composite functions. Okay, so forget about the cubic root function and just look at this 4x cubed plus 3 raised to the 4th power. How many functions?
2.
How many chains?
1.
1. Okay, good. We'll come back to that in a second. This one, the cubic root of 2x plus 1. How many functions? 2. How many chains? 1. Okay, so now we have a product rule. So the product rule says the first times the derivative of the second plus the second times the derivative of the first. So what do we get? We get a question mark, which is... Okay, the first... Yeah, let's go back there again. Okay, now there we go. 4x cubed plus 3 raised to the 4th power. The first times the derivative of the second. So this thing is 2x plus 1 raised to the 1/3 power. Now take the derivative of this. And you told me there were two functions there. The function on the outside is the 1/3, so I take the derivative 1/3 times 2x plus 1 to the negative 2/3 power. Chained on with a 2. Where'd the 2 come from? Good, it's the derivative of 2x plus 1. Okay, that's the first half of the product rule, plus the second times the derivative of the first. So 2 functions, 1 chain. Bring the 4 down. Reduce the power by 1. Chain on 12x squared. At this, go ahead.
Sorry. So those we just do the product rule, except when we multiply it, we have to do the chain.
Yep. Okay, so before I move on to the next little tidbit of fun with this function, is everybody okay with the chain rule and what we did there? Go ahead.
So you did the product rule, but when you needed to take the derivative of it, you used the chain rule.
Well summed. That's a good summation of what just happened. I'll say that again for all the folks at home.
You did the product rule, but when you needed to take the derivative, you used the chain rule to get the
Good. Okay, now, Haley?
Why do you use the chain rule instead of just taking the derivative?
Because in order to take the derivative, you've got a function inside that also needs to be addressed. Okay, so the difference would be if I had a function like x squared, all right, this is going to seem like an oversimplification of your question, but I'm going to do it anyways. We actually use the chain rule when we take the derivative of this. But it's, okay, we go all the way back to algebra. X is actually the same thing as 1x raised to the 1st power, right? But being intelligent people, we don't use the ones all the time, so we just write x. Same thing happens here. When I take the derivative of this function, I actually have to use the chain rule, and I get 2x times the derivative of the inside function, which is just x, which is a 1. And we don't need to keep writing 1s over and over again. So initially we learn the power rule and don't even talk about the chain rule. Now we have to start doing the chain rule because I have a function in there that's other than something simple like x. I might have something like 2x minus 3 or 2x plus whatever it is. Okay, good. Anything else about the process before I show you the algebra of simplifying this beast? You'll notice that each of the two terms, and the terms being here and here, have common factors. So we want to factor those things out. And this is a necessity because later on when we start looking at a whole bunch of different things. We're going to want to express this derivative as a product, not as a sum. Okay, because I got the plus sign in there. So what do these two terms have in common?
They're large.
Good. Astute observation. Come on, algebra 1. What do they have in common, Mark? More so than that. A little more. Nope. Here's one. There's a 4x cubed plus 3 there. There's a 4x cubed plus 3 there. Now you understand my question? Okay, good. So I'm going to start by factoring out a 4x cubed plus 3. Whoops. Now the question is, which power do I take? There's a 4 and there's a 3. The rule is always take the more negative or the smaller power. So I'm going to take out a third. All right, I'll come back to that in a second. Then I've got 2x plus 1 raised to the negative 2/3 or raised to the 1/3. Again, always take out the more negative power. Okay, those are the things they have in common. Now I got to do some cleanup. If I took 3 of the 4x squared plus 3 out of here, and there was 4, I'm left with 1 there. The 2x plus 1 raised to negative 2/3 left, and I'm left with a 2/3 in there. Plus.
Why are you left with the 2/3?
There's a 2 back here, and there's a 1/3 in there.
That makes sense.
Okay. Now the second one. The whole 4x cubed plus 3 to the 3rd power got pulled out in front, so that's gone. I have a 2x plus 1. And if I have a 2x plus 1 raised to the 1/3 power, and I took out a 2x plus 1 raised to the negative 2/3 power, what does the exponent become here? It's 1, correct, and that's why we take the more negative exponent out. So that's gone, and I'm left with a 48x squared. And that was fallacious. C.
So do we have to simplify it like this for every product?
For everyone, not necessarily, but it's a precursor to what's going to come up. Because now I have a product. I've got this 4x cubed plus 3 to the 3rd power times 2x plus 1 to the negative 2/3 power, and then that monstrosity inside, which I should probably simplify, but I'm not going to take the time right now because I'm going to move on to bigger and better things. Okay. Any questions before I erase this beast? Going once, going twice. Done. So we just did that already, but let's go over it again. Two functions, one chain. So one function inside is a quotient, and so we have to do a quotient rule, and this is where you start to realize that, and I'll show you in a second, how we can change a quotient rule into something else that we can work with. In fact, let's do that before I get into this beast. Let's suppose I have a function, we'll do something easy, 1 over x plus 3. And I ask you to take a derivative. Okay, well that's a quotient, so I'd have to do the quotient rule. Okay, so x plus 3 squared on the bottom, bring the x plus 3 to the top, take the, do all that business. However, I can rewrite this as x plus 3 to the negative 1st power. Now it becomes a chain rule, and you can do it as a chain rule. When you're done, the two functions might look the same, they might look different. The important part is they're equivalent. So if I do the chain rule over here, I would get x plus 3 quantity squared, x plus 3 up on top, times the derivative of 1, which is 0, that disappears, times the numerator times the derivative of the denominator, which is 1. So I get that goes away, and I'm left with -1 over x plus 3 quantity squared. That's if you chose to do a quotient rule. If I chose to do a chain rule, then bring the negative 1 down in front, reduce the power, rewrite it. Well, that's a plus. Oh, look, same. Okay. Same results, different ways to approach the problem. And it doesn't matter what technique you want to use. You want to turn a quotient into a product, go ahead. You want to do it as a quotient rule, go ahead.
Did you take a chain from
Here?
Yeah.
Yes, but I didn't bother showing it because it's 1, right? So it doesn't matter. Okay, let's look at this big monster. How about that guy? All right, tell me what happened there, other than the fact that I just clicked once on the remote. Where did that beast come from? Got it.
You brought the 2 to the front, and then
Mhm.
the exponent became 1, and then you took the derivative using the quotient rule to make the big thing on the right.
Beautiful. You're having a stellar day today, Connor. Must be the bow tie.
Yeah, probably. Maybe it's suspenders too. I'm just not wearing them.
Why would you wear suspenders and not wear them?
I don't know, he's pretty lame, I think.
I
It's
accept
like
my shorts,
suspenders are
red
out,
shorts
so.
now.
I think she just called you up.
Yeah, but they kinda
You have a belt on too?
No.
Okay.
He's about to go for it.
He what?
He's
He's got a belt. Yeah, he's got a belt on, but it's unbuckled, along with his suspenders. That's great. Anyways. Okay, what just happened there? Yeah, because it says simplified, good. I cleaned up the numerator of that big beast. Then multiplied the denominators together. And stopped there. So there's not much I can do there. If multiplying this puppy out is not going to get me anything constructive, it's going to give me a big ugly quartic. It's not going to allow me to simplify anything. There's nothing to cancel with the denominator, so you just stop there. Mark.
Where did that cube come from in the bar?
Multiplying this squared times the denominator over here. Question?
Can this chain rule like stand alone, or is it always connected to one of the other rules? I'm just kind of confused what it's like, why we use it.
It can stand alone, yeah. When you have a function within a function, is what it allows you to take the derivative of composite functions.
So that last part is the chain? Like that whole big...
Correct. Yeah. This is the chain of this quotient. Okay?
You go back.
Oh, sure. No problem. Life wouldn't be complete without a little bit of trig. Most people would. The trig actually here isn't too bad because it's just taking the derivative of trig functions we already know, but then we have some chains stuck onto it. Okay, now we good? Okay. This stuff you knew already, just a quick refresher, or you should know, the derivative of all 6 of the trig functions. So now what happens when we want to take the derivative of something like that? All right, how many functions are going on there?
2.
No.
3.
3. How many chains?
2.
2. What function is on the outside? The squared, the sine, or the 4x to the 5th?
Sine.
On the outside.
Sine.
Say again.
Sine.
Nope. The squared term. Because remember, that sine squared is actually the sine of 4x to the 5th, all of that squared. Okay, so what's the derivative? What do you do first, other than cry? Yeah, move the 2 to the outside. Stop it. I lost control. Okay, here we go. Bring the 2 to the outside. All of that stuff inside. Reduce the power by 1 and it becomes this. First chain, which is the next function inside, moving inward from the squared. Sine. What's the derivative of sine? Cosine. Of this stuff still. Second chain, inside most function. 4x to the 5th. Now, how to clean this up? It's a little sloppy to leave stuff on the back end. We usually want to move that to the front. So if I was cleaning this up, I'd get 40x to the 4th times the sine of 4x to the 5th times the cosine of 4x to the 5th. And I'm all done. Great.
I'm just confused on how you know that the square is the first, or it's the outside one.
Because if I rewrite that function, it's actually this.
Oh.
Putting the 2 in there is just a different fancy way of doing it so that you don't get... Why do we write the squared in there? It's so that if we were to write it the other way, you would get confused with what's squared. So that the notation is to bring it in there, but it's the same thing as this guy here. Okay? So the outside function is a squared, the next one is a sine, the next one is the 4x to the 5th. 3 functions, 2 chains. Yeah, I know. Okay. Now, this, for some reason, your book loves this identity. There was this obscure identity in, not obscure, but there's a trig identity called the double angle identity that says that if you have 2 times the sine of something and the cosine of something, you get that. It's not the end of the world if you don't know it, but I just don't want you freaking out when Bob has a different answer than you, because that's where he would get that answer, by using that identity. Now, what I have here is all the stuff we've done with derivatives so far. So we're pretty much done with derivatives, and then from this point on, we just practice. Practice, practice, practice. Chain rule, chain rule, chain rule, quotient rule, product rule, all that fun stuff. All of this stuff should look familiar. The only problem is this is the fancy schmancy calculus talk. You might know some more eloquent ways of doing this. But constant product rule, derivative of a sum is the sum of the derivatives, quotient rule, product rule, constant rule, all 6 trig functions, the power rules up here, and then, of course, today, the chain rule with the FU. Okay. I knew you couldn't control yourself and start laughing. All right? Chain rule is going to cause some frustration. You just have to keep practicing, keep trying it over and over again, checking your answers to make sure you're doing it correctly. Just because your answer is different than what Bob has doesn't mean you did it wrong. He may have just simplified things a little bit more to get to his answer. Okay?